Alright, hey everyone, welcome back to the channel. In this video we're going to go through the new numeracy standard, so that's that 10 credit paper US32406 where we're going to use mathematics and statistics to essentially look and solve numeracy problems. Alright, oh, and one thing I better mention before we start, this paper, there is no mark schedule that's been released to the public, I guess, and so all these answers are coming from me, and so you should definitely seek verification if something doesn't sound right to you, but I hope everything will be okay. So let's get into it. So question 1, a walk around Lake Tsikitapu. So Jess is driving from Rotorua to Lake Tsikitapu. The dotted line on the map shows the road. Part A, in which direction is Jess driving? So what we have here is, if I highlight this in red, we've got Jess, and she's starting here in Rotorua, and she's making her way to Lake Tsikitapu, and she's going to take this route essentially in this direction, right? Because she's starting at Rotorua, and she's ending up at the lake. So the first thing we're going to need to know is obviously which direction that she's traveling in. We're going to need some kind of compass, right? So you can see on the top here, they've given us part of the compass, right? Which, up is pointing to the north side, right? So what we're going to need to do first is we're going to need to label each of the axes, which way is north, which way is south, and whatnot. So how do we do that? Well, we need to use our favorite Kiwi acronym, never eat soggy Weet-Bix. So what does that mean? It means we go around in a clockwise fashion and we write down the first letter of that acronym. So never is for N for north, eat is E for east, soggy is for south, and W, Weet-Bix is for west. So what we've got here is never eat soggy Weet-Bix. Right, so we're just pulling the first letter from that acronym, right? So that's for north, east, south, and west. Okay, so now we've labeled our compass. So now we need to know what direction she's traveling. So like I said before, she's starting here and she's ending up here. And so the general direction that she's traveling is kind of in this diagonal line, right? So what we're going to do is we're going to go up to our compass up here, and I'm going to redraw that line in the same direction. So it's sort of like this, right? All right, cool. So now we need to know, what direction is this arrow pointing? And now remember that I've drawn the arrowhead this way because that's, her ending destination, right? So which direction is the arrow pointing? It's in between east and south, right? So that tells us it's either going to be east-south or southeast. So, which one is it? So all our directions, when they're diagonal, are going to start with north or south. So they never start with east or west, right? So east-south and, I guess, west-south, and also west-north and east-north. These are wrong, right? We never start with east or west. We always start with north or south. So if I cross that out, we're in between east and south, but we never start with east. So that means that we're going to have southeast, right? So we know that it's going to be southeast or east-south, but southeast sounds more correct, right? And southeast is correct, right? So direction that she is traveling is indeed southeast. And the reason for that is because it's in between east and south, right? So hopefully that makes sense. Part B, we're going to use a scale on the map to estimate how many kilometers that Jess is traveling. So I'm going to remove that. So where's our scale? Our scale is down here at the bottom. We got this specified distance here, and that's 2 kilometers. So what I'm going to do is I'm going to estimate, draw that distance on our graph so many times until we reach the destination, and then we're going to have so many segments of 2 kilometers. We're just going to count them up and add them together, and that will give us the total distance. So if we start here, and remember that we're going in this direction. If I draw this line here, this is about the same distance as that. So that's our first 2K. And then we're going to do another line of similar distance. Now, careful here, we've got a curve, so we need to take that into account. So I'm going to say, well, this is about another 2Ks approximately, give or take. So this is segment 1, for example, and this is segment 2 now, for example. So let's do, we've still got room, so we need to keep moving towards the lake. So if we draw another 2Ks, well, this is about another 2Ks here. So this is our third segment now, right? Our third segment now. And we're going to keep going. So we're going to do another 2Ks, approximately here, right? So that's good. So that's our fourth segment. And then we've still got about another bit of space. This is, give or take another 2Ks. So we've now got 5 segments of 2Ks, right? So what I mean by segments, well, this was 2Ks, this was 2Ks, this was 2Ks, this was 2Ks, and this was 2Ks. So if we want to know the total distance traveled, we're just going to sum up or add up all our segments, right? So this is 2, sorry, I better write this here. This is 2 plus 2 plus 2 plus 2 plus 2, which is the same as 2 times 5, which is equal to 10 kilometers. So we're estimating that she's traveled approximately 10 kilometers. All right, let's take a look at part C. The walk around Lake Tikitapu is 3.6 kilometers long. A friend says that the walk takes about 25 minutes. Jess knows that the median walking speed is about 4 kilometers per hour. Does the friend's estimate sound reasonable? Explain your answer. So, I guess one thing that I've noted from these numeracy papers is that you can solve most number questions using ratios. And so what I'm going to do is I'm going to go through quite, I guess, reasonably in depth for this part, how I would solve this using a ratio, or solve this using ratios, and then we'll use this technique that I've shown you throughout the rest of the paper. So the first thing that we're going to want to do is establish our word ratio, right? So if I write down my steps, 1, write down word ratio. So how do we identify our ratio or our rate, technically in this case? We're looking for keywords like per and to. So we're looking for per or to. So these relate two things together, right? So if we look in the question, we can say we've got 4 kilometers per hour is the walking speed. So that's our known ratio, right? So, or technically it's a rate. So our rate is 4 kilometers per hour. So what's the word version of this? Well, what are we comparing? We're comparing kilometers to hours. So we could write this down as our word ratio, kilometers to, and our ratios use the colon, to hours. Okay, now I've written hours here, but I'm actually going to change that to minutes. And the reason why is that, if we look at the sentence before that, we see that we're talking about 25 minutes. And so that's going to come in handy a bit later on. So note that we can interchange between hours and minutes quite easily. So we're comparing kilometers to minutes. Or we could do kilometers to hours. It's completely up to you, but I think it's going to be easier if we look at minutes. So what's the next thing that we're going to do? So the next thing we're going to do is write down the actual ratio. So write down the actual, maybe I'll put the numerical or number ratio or rate. So how many kilometers do we have? So if we look at our word ratio, we've got 4 kilometers per hour. So we're looking at 4 kilometers. And that's related to how many minutes? Well, it's per hour. So we're looking at 4 kilometers to 1 hour, and we know that 1 hour is 60 minutes. So we're looking at 4 kilometers for every 60 minutes. Cool. So what's the next thing we're going to do? So the third thing that we're going to want to do is write down our final ratio, or write down, we'll go with final, but it's really an unknown ratio, right? So I'm going to write down our final, I put final in apostrophes, ratio. So essentially, what are we trying to get to, right? Or what is the unknown thing that we don't know? So if I was to draw another ratio under this one, so I've got my colons there, and I'm going to need to put 2 things in here. So essentially, right, we want to know how long it's going to take to walk around Lake Tikitapu, right? So we know that Lake Tikitapu is 3.6 Ks. So we know the kilometers, right? We know it's 3.6 Ks. How many minutes is it going to take? A common thing that you might get tripped up on is looking at this 25 minutes here and putting, it's going to take 25 minutes. This is not true, right? This was what the friend was assuming or making a prediction on, right? We want to know the actual time it takes to walk around Lake Tikitapu, right? So if we know the walking speed here is 4 to 60, how many minutes is it going to take if we want to walk just 3.6, right? So actually, we don't actually need to even work out the ratio in order to figure out, how many the friend estimate is reasonable. 3.6 is not that much lower than 4. If we know that it takes 60 minutes to travel 4 Ks, it's going to take a little bit less than 60 minutes to travel 3.6 Ks, right? And so 25 minutes, that's like less than half of like 4, right? So we already know that it would take 30 minutes to travel 2 Ks, right? So the friend's estimate is definitely incorrect. However, we're going to work it out fully. So now that I've written down our final ratio, so in all honesty, we don't actually know what this is yet. We want to work that out. That's what we're trying to figure out. So this is our unknown. So how do we work this out? So the technique that we use, so part 4 is the most important part, is we multiply both sides by, we're going to say the bottom of unknown divided by the top of unknown. Right, so what does that mean? So essentially, we're going to multiply both sides of the ratio. So we're starting from here and we're trying to end up at this kind of final ratio, if you think of it like that. So we're multiplying both sides by the bottom of the unknown, which is 3.6 is the bottom of our unknown fraction. So multiplying by 3.6 divided by the top of the unknown. Sorry, it should be the top of, that same side. So what side is it on? It's on this side, so we're looking at this side here. So we're dividing by the top of the same side, which is 4. Okay, so we're dividing by 4. So what's 3.6 divided by 4? It's 0.9. So we're multiplying by 0.9 on both sides. So this is the same as 0.9, so I'll just rewrite it as 0.9. And we can double check this by going 4 multiplied by 0.9. We end up with 3.6, which is correct. And if we multiply by 0.9 on the right-hand side, so 60 multiplied by 0.9, we're going to get 54. So it takes 54 minutes to travel 3.6 Ks. So the friend estimated it would take 25 minutes. This is clearly wrong because we got 54. So now we can write our answer. So friend's estimate is wrong. It will take 54 minutes to travel around Lake Tiki-Tapu. Right, and so that is how essentially we can approach any of our number questions using ratios. We first write down the word ratio, we write down the number ratio, we write down our unknown or final ratio, what we're trying to get to. And then we need to multiply both sides by the bottom of the unknown divided by the top of that same side. And I'll show you another example in the next question of what that means. All right, let's look at question 2. This question's on buying taro. Taro costs $7 per kilogram. What is the cost of a taro that weighs 510 grams? So again, we're going to use our ratio technique that we learned in the last question. I'm going to go through it a bit faster now. So essentially, what's our word ratio? Well, we're comparing cost to kg. So, but also, if we look here, we're looking at grams, right? So it's going to be easier to make a comparison in grams if I convert this kg to g, right? So let's look at a comparison between dollar to grams, right? So this is technically our word ratio, right? The next thing we're going to want to do is write down our numerical version. So how much dollars compared to how many grams? So we're looking for our ratio. Our ratio in this case, or our per keyword, is in this sentence here. So this is our ratio or our rate. So how much dollars? $7. And that's relative to 1 kilogram. And also note that 1 kg is the same as 1,000 grams. So this is 7 to 1,000. So $7 to 1,000 grams. So now we want to know how much a taro will cost if it weighs 510 grams. So if we write down our final or our unknown ratio, we know that it's going to be 510 grams, and I'm writing this on the gram side, so make sure it's on the correct side. That's why we write our word ratio here. And so how much money is that going to cost? Well, we don't know yet. That's what we're trying to work out, right? And so how do we work that out? We're going to multiply both sides by the bottom of the unknown. So what's the known side of our unknown? It's this side here. So multiplying both sides by 510 divided by the top of that same side. So what's the top of, so we're looking at the gram side, the top of it is 1,000, so we can divide by 1,000. We're doing this on both sides. So we've got 510 divided by 1,000, which is the same as 0.51. So we're multiplying both sides by 0.51. So if we do 1,000 times 0.51, we get 510. So that looks like it is correct. And what's 7 times 0.51? It's 3.57. So that means that 510 grams of taro costs $3.57. And that is our second option here. So I'll give that a tick. Part B, a taro costs $4.20. What is the weight of the taro in grams? So we're going to do the exact same thing pretty much. We've got a dollar to gram comparison. We know that a taro costs $7 per kilogram. So we know it costs $7 for 1,000 grams. And so now if we change this money, or the cost to $4.20, how much is it going to weigh? Well, we don't know what it's going to weigh. That's what we need to work out. So how do we work that out? We're going to multiply both sides by the bottom of the known side of our final ratio, and that known side is the $4.20. So we're multiplying by $4.20 divided by the top of that same side. So what's the top of that side? It's 7. So we're dividing by 7. So what's $4.20 divided by 7? It's 0.6. So we're multiplying by 0.6 on both sides. So if I go 1,000 times 0.6, it's 600. So 600 grams costs $4.20. Now, one thing just to point out, make sure that you get your conversions correct, right? So we've got kilogram here, but we've got grams here. So we need to make sure that whatever unit we pick, like we could have picked kgs for this as well, but it always needs to be the same for all of our comparisons. Okay, part C. The table shows the weight and the costs of 3 taro. Mark the points for each taro on the graph below and draw a line through the points. Continue the line to the edges of the graph in each direction. So we're just going to make a plot here. So let's mark, so our weight is our x-axis, right? And that means our cost is our y-axis. So essentially when we do a plot, we look for which value we go across first, the x-axis, until we match the number that's listed in the table, and then we go up and match the cost as well. So for our first point, we're looking for 500 grams. So we always go through the x first. So 500 grams is here, I believe. So 500 grams is here, and then we go up to 3.5. So up to 3.5 is here. So we're trying to get to this point here. So this is where our first point is located. Let's do the next one. 1 kg is the same as 1,000 grams is costing $7. So 1 kg or 1,000 grams costs $7. So I'm going to go all the way up to 7 there and make my point. Okay, so that's 2 plots done. And then finally, our third point is 250 grams at $1.75. So if we look at 250, that's going to be this point here, in between 200 and 300, or halfway in between them. And then we're going up to $1.75. So $1.75. So this would be $1, this would be $1.50, this would be $2, and therefore this is $1.75. So if we go $1.75 through up to, 250, it'll be that point right there. So we've got this 3 points on our graph. And then what they want to do is connect all the lines together and continue the lines to the edge of the graph. Now, this should be a linear relationship. So if we draw a line, we should just keep it going all the way. And I should have kept this going Hopefully that looks straight. So the cool thing about this is that you actually only need 2 points in order to plot the full graph, right? But they've given us 3 points, so we better do that. But that's our graph. And here's part 2. Mark a 4th point that lies on a line with an X. Explain what this point shows about the cost of taro. Okay, so we can make a point on any part of our line. I'm going to go, and I'm going to say this point here. Yeah, let's go for this point here. So we're going to mark it with an X. And what does this X tell us? It tells us that when the weight is 700 grams, it costs what looks to be around $5, right? So my answer is going to be when the weight of a taro is 700 grams, the cost of the same taro is approximately $5. And that might not be exact because I haven't drawn my line completely straight, but we can actually work it out if we wanted to. So for example, we know using our ratios we've got 1,000 grams related to $7. So if we want to know the weight of 700 grams, we're going to multiply both sides by 7 over 10, or 0.7. So what's 7 times 0.7? It's 4.9. So it actually costs $4.90. But yeah, we could also say, what else might we want to say? We might say there is a positive linear relationship between weight and cost. Between weight and cost. So what does that mean? Essentially, as we increase the weight, our cost is also going to increase, right? And that's why we have this kind of positive, we say it's positive, kind of gradient or positive steepness or slope. So if our graph looked like this, then that's negative, right? Because as our weight increases, the cost would be decreasing. All right, let's look at question 3. We're looking at bank balances. Sam works part-time while he studies. Below is his bank statement. So debit means that money goes out of his account. Credit means money's going in, and balance shows how much is in his account. So, question A. Why does Sam have a balance of negative 108.41 at the end of the 18th of Feb? So, if we look at the 17th and the 18th of Feb, this is going to give us a key, right? So he ends up having negative 108, right, in his bank account. So at that point, so before the negative 108, he has $398 in his account. But then what happens is that he has a debit of $506 to these motorcycle repairs, right? So he has to pay. So debit means that he's paying this money. He's transferring this money out of his account to the motorcycle repair place, right? So he's losing out on $506.4. So he's paying that amount, right? But he didn't actually have that amount. He only had $398 in his account, right? So, yeah, essentially, if we were to do that mathematically, he only had $397.99, and then he lost, or they took out $506.40 from his account. 397.99 minus 506.40 will give us the remainder, which is indeed negative 108.41. So he's now short negative $108.41. So, which could be the answer? There is $108.41 left in his bank account. This is definitely not the case. he owes the bank $108.41. This is true, right? So he didn't have $108.41. I guess the bank has paid that on his behalf, right? So he actually owes the bank that money back. He used money which wasn't his. And so I would say that this would be the answer. The bank's not charging him a fee. He's not paying a fee of $108. Now, Sam has $108.41 in bills that must be paid. I don't know. So he's already paid for it. Well, the bank's already paid for it on his behalf, I'm assuming, right? I don't have the mark schedule. So this one's a bit, it's not very clear, but I would say it's probably the second one. But, I might be wrong. Let me know if you think otherwise. Now, part B, the balance at the end of the 19th of Feb is missing. What is his new balance? So essentially, if we look at the 19th of Feb, if I remove this here for a second. So if we're at the 19th of Feb, he's getting a credit of $517. So essentially what a credit is the money goes in, so we're going to add that money on. So if we look at his balance before, it's a negative 108.41, and then we're adding this amount on because it's a deposit, it's going into his account. So we're adding $516.90. So what's negative 108.41 added with 516.9? You can use a calculator for that, or you can do it by hand. It's up to you. We're going to end up with $408.49. Okay, and let's double check that I've done the math correctly. So 408.49 added with 108.41 should give me 516.9. Good. So essentially, why is this number less than this number? It's because he owed that money to the bank. So when the money's gone into his account, that money's being paid off or given back to the bank. So his new balance is $408.49. Should Sam be worried that he is spending more than he earns? I believe the answer should be yes. If you're spending more than you earn, you should definitely think about what you're doing. So explain your answer using information from the bank statement. So I guess if we say, I don't really know what they're looking for here. Sam's bank account was in the negatives, meaning he owed the bank money, right? Generally speaking, I don't know, this is bad practice because he is using money he does or he may not have. Again, no mark schedule, so this is my opinion. Let me know if you think otherwise. Alright, let's look at question 4. We're looking at whale watching. So we've got a table here which shows the number of whale sightings for March. So we've got different whale species and the number of sightings. Part A, select the graph types which will be suitable for displaying the data in the table, and there is more than one correct answer. Alright, so what I'll do is I'll go through each type of graph and explain why or why not it would not be suitable. But first of all, let's just look at what kind of data we have. So whale species, is this categorical or numerical data? Well, we're categorizing whales into different categories. So this is categorical data. And if we look at the number of sightings, are we looking at putting things into categories or is it numerical? It's numerical data, right? We're looking at the number or the count of that specific whale. So we've got categorical data and we've got numerical data. So first thing, line graph. So what is a line graph used for? Well, essentially a line graph we usually use a line graph when we've got like data which is related to each other, right? And usually that is numerical or like a time series kind of thing. Essentially, can we relate sperm whales to orca whales over time or something like that? No, that doesn't really make sense. So I would say a line graph does not really match this data here. What about a scatter plot? Well, scatter plot compares two numerical data, right? So two variables of numerical nature. For example, height and width, or I don't know, body weight and height. We've got one numerical but one categorical, so it's definitely not this either. Now, what about a dot plot? So a dot plot we can use essentially to display this data, because we can put our categories on each, I don't even know what you call that, on each step. So we could have orcas here and then sperm whales there, and then put our numerical data up here. So how much count, or how many of each type of whale was seen. So yes, we will put a tick there. And now if we look at a strip graph, can we use a strip graph to show this data? I would say yeah, we can. The reason is we can look at the percentage. So if we look at this as the total number of sightings, so if that was 100%, then we could look at each of these points as like a proportion. So this is the proportion of like sperm whales, and this is the proportion of orcas, for example, and so on and so forth. So that would be okay, because we're doing a categorical comparison of proportions. So I would say that would be fine. And finally, pictograph. Could we use a pictograph? Well, essentially a pictograph is very similar to a dot plot, right? So we could put these as our categories, and this is our count of whales. So I'd say that's fine as well. So part B, data of whale sightings for 3 different months are shown in the graph below. In which month do you have the best chance of seeing all species on a whale trip? Okay, so if you want the best chance of seeing all species, then we're going to want to pick the month which is the most uniform, right? So, or has the all species, with a big, relative amount of sightings. So if there is a month where their sightings of like some type of whale is really low, then we're not going to be able to have a high chance of seeing all the species. So we're going to not pick that month. So if we look at the month of March, well, there's high, probability of seeing sperm and orca, but look at our humpback. We barely saw any, only like, what's that, 5 or yeah. So no, probably not this one, right? If we look at July, we have got good sightings of sperm and humpback, and medium probability of seeing orca and other whales too. So July's looking reasonably decent. Let's just have a look at November to check. So November, sperm is okay, orca's okay, others okay, but yeah, our humpback is really low in the November month as well. So I'm going to pick July is where we're going to have the best chance of seeing all of our whales. Now part 2, sperm whales and orca have teeth, but humpbacks do not. Which 2 months have the most sightings of toothed whales? So which whales have teeth? Sperm and orca. So we're picking the 2 months which have the most sperm and orca sightings. So these are the first 2, the stripes and the dots. So which months have the most sightings of sperm and orca? So we can either add them up or just look by seeing, but if we make a comparison, I can clearly see that these 2 are going to have the most. So yeah, I'm not going to count them. You can count them if you want to see what the total number of sightings is, but it should be March and November. So if I'm wrong though, do let me know. March and November. Oh, and they ask us to support answer with information from the graph. So let's actually do the number of sightings. So we'll go toothed whale sightings in. So if we look at the toothed sightings in March, that is going to be, we are looking at sperm and orca, right? Yep. So we're looking at 110 approximately, and about, let's say 75 here. So 110 plus 75 is 185. And then in July, we are looking at a little bit. Let's say that's 115. This is probably not actually 110, to be honest. This is a little bit less, but all good. 115 plus maybe like 42. 157. So we'll put it here for approximately 157. And then November is approximately let's go 105, and then this is let's just say 70. Why not? 105 plus 70 should be 175. So yeah, March and November have the biggest number of sightings, and that's why I've picked it. Alright, let's look at question 5, getting there. Below is a diagram of a train network. Each mark is a station, so these are stations. You catch the train at the Kiwi station on the West Line, so you're going to catch the train here and get off at the Penguin station, which is here. The train stops at every station. How many stops are between Kiwi and Penguin stations and do not include Kiwi and Penguin? So I've marked my Kiwi and I've marked my Penguin, so what I'm going to do is count the number of stops in between. So just a counting exercise, 1, 2, 3, 4, 5, 6. Well, there's 6 in between, right? So I'm going to tick 6, right? So 1, 2, 3, 4, 5, 6. Yeah. So just a reminder, these are stations, so the little slashes are stations, so we're not counting these arrows or anything like that. Pretty self-explanatory. Now here is part of a timetable for the West Line. You want to get to Penguin just after 10. At what time should you catch the train at Kiwi? So remember that we're starting at Kiwi and we're trying to travel all the way to Penguin. And so hopefully we travel from Kiwi to Sparrow to Moa. I'll just double check that. Kiwi to Sparrow to Moa and so on. Yeah, so the train moves in this direction. So if I just make this clear, this is the start and this is the end point. So if we want to get to Penguin just after 10, we better start at 10 o'clock at Penguin and then work our way back to determine what time we should catch the train at Kiwi. So if we look at Penguin, if we want to get there just after 10, we're going to go at our Penguin column and look for a number which is over 10. So if we go down, we can see here we've got 10 past 10. So that's just past 10. That's the first train after 10. So we're going to want to essentially get on this train line, which is kind of going down this way here, right? So as a side note, if we look at it, so this is, each time is like a new kind of route, if that makes sense, right? So this is one line, and then this is like another loop, this is another loop, and so on and so forth. Okay, so essentially we've established that we want to arrive at this time here. So if we just trace back all the way to the start of Kiwi, we can see that if we get the Kiwi train at 9:48 a.m., we should arrive at Penguin just after 10, or at 10 past 10. Now, how long will the train journey take between Kiwi and Penguin? So essentially, if we are getting on at 9:48 and arriving at 10 past 10, so I guess there's a few ways you could do the maths, but essentially if we just round up to 10, so how long does it take? I'm going to break this down from going from 9:48 to 10 o'clock, and then from 10 o'clock to 10 past 10. That's, so how many minutes in between 9:48 to 10? Well, that should be 12 minutes, right? Because there's 60 minutes in an hour. So 12 mins there, and then from 10 to 10:10, there's just 10 minutes. So we're going 12 plus 10 is equal to 22 minutes. Okay, so it should take 22 minutes to go from Kiwi to Penguin. That looks good to me. So if we just verify this, if we're at 9:48, we go 10 minutes, that's 9:58. Another 10 minutes, that's 10:08 plus 2 is 10:10. Yeah, so that is correct. All right, question 6, we're looking at netballers. So we've got a graph here that appears in a sports magazine. We're looking at the height of silver fir netball players in the 1987 World Cup squad. The question is, what is the height of the tallest player in the 1987 squad? So essentially our heights are increasing from the smallest to the highest. So if we look at our highest here, it's going to be the dot furthest to the right, which is this one. Now what's the height of this player? Well, it's in between 184 and 186, so the height must therefore be, what's in between 84 and 86? It's 185, right? So that means that the tallest height is 185. Now this graph shows the height of the players in the 2019 squad. On the horizontal axis, mark the median height of players in 2019 squad with an X. So what's the median? The median of a data set is the middle number. So essentially we need to compare sorted data and then chop off all the ends until we reach that middle number. So what have we got? We've got 173, we've got 174, we've got 178, we've got 181, we've got 184, we've got 4 lots of 186, so we have to write that in. 186, 186, 186, 1, 2, 3, 4, 5, 6. Oh, sorry, we've only got 4 of 186, that's my bad. So 4 of 186, and then 3 of 188. 188, 188. Actually, what I'll do is I'll shrink this because we want it in one straight line for demonstration. So I just better double check I've done that correctly. So 173, 174, 178, 181, 184, 4 lots of 186, 1, 2, 3, 4, and then 3 lots of 188. Alright, so we're going to start cutting off from the ends until we reach the middle number, and that will tell us what the median is. So 173, 188, 174, 188, 178, 188, 181, 186, 184, 186, and now we're left with 2 numbers in the middle. They both happen to be, 186, right? And so when we have, 2 numbers in the middle, we add the numbers and divide them by 2, but because they're the same number, I know that my middle number is still going to be 186. So my median is 186. So mark the median height, it's here. Part C, the graph shows the height of players in the 1987, 2003, and 2019 squads. So the sports magazine article says the height of Silver Fern netballers has increased over the last 32 years. Explain whether you agree or disagree with the statement or cannot decide, and we've got to use information from the graph. So I guess the first thing I'll do is I'll draw the shape of our graphs. So yeah, it's quite interesting. If we look at it from a whole data set, there the data's kind of peaks. And sort of, the peaks between 1987 and 2003 are quite similar, but then you've got this kind of big peak here at the end, and then the larger peak is kind of here in 2019, right? So here's the thing. Can I agree with this statement totally? The height of Silver Fern netballers has increased over the last 32 years. Honestly, it's hard to say without more information, to be honest. I don't know... I don't know if these players here have become these players here, in terms of positions and whatnot. But rather, let's look at the average, and let's look at making a comparison of the average, and we can make a comment on the average height, assuming that this is the full data set, right? So if this was not a full data set, if this was just a sample of the squads, then definitely we cannot make a call because there's so much overlap between all the data. However, if this is the full data set, then we might be able to make a comparison with averages. So let's look at the average height of 1987. So how do we do that? We sum all the data points up and then divide by the number of data points. So we've got 171 plus 171 plus 175 plus 175 plus 176 plus 176 plus 176 plus 178 plus 178 plus 183 plus 183 plus 185. So that gives us 2127. We're going to divide that by 2, 4, 7, 9, 11, 12. So the average height is 177.25. I hope I did that correctly. What about for 2003? I'll do it in my, I'll just do it quickly. Okay, so what I've done is I've gotten my averages. My average height seems to be increasing as the years go on. So what I might say here is the average, and I'll definitely highlight average height of silver ferns has indeed increased over the last 32 years. Okay. However, there is so much overlap between all the data, we cannot say for certain that the height of all, silver ferns, we say due to the overlap. So we'll say due to the overlap, we cannot say that the height for all silver ferns has increased over time, right? And so I don't have a mark schedule here. I would say they need to really give more information than the question about what they're looking for. This is just my opinion. Hopefully it's good. If you want to add anything, leave it in the comments below. All right, let's look at question 7. So this is about Lisa painting a bedroom. They give us the dimensions of the bedroom here. The first part is, what is the area in square meters of the shaded wall of Lisa's room? So remember, the area is base times height. So what's the base? So this is our shaded square. What's the base of the shaded square? Well, we know that this is the height. So this is the height. I'll label that h, and therefore this must therefore be the base, or the other side, right? So yeah. What is the area in square meters of the shaded wall? It's just going to be the height multiplied by the base. So what's 2.4 times 4.6? That is 2.4 times 4.6 is 11.04 meters squared. Cool. Part B. Lisa knows that 1 litre of paint will cover 6.7 meters squared. The ceiling has an area of 18.4 meters squared. What calculation does she need to do? So again, another ratio question. So using this technique I taught you before, what is our ratio? It's given here. So a litre of paint is related to 6.7 meters squared. So if we look at litre to area, for example, or paint to area, we are looking at 1 litre covers 6.7. So if we want to cover 18.4 meters squared, how much paint do I need? Well, I don't know. That's what I want to work out. So to do that, I'm going to multiply both sides by 18.4 divided by 6.7, because this is my known of the final ratio, and I'm going to multiply by 18.4 divided by the top of that same side, which is 6.7, right? So go back a bit earlier if you want to, in depth of how I would solve ratio problems. But what's 18.4 divided by 6.7? It's 2.75, right? So multiplying this side by 2.75, or 18.4 divided by 6.7, I'm going to get 2.75. So 2.75 litres will cover 18.4, an area of 18.4. So what's the question? What calculation do we need to work out? So what was the calculation, the ultimate calculation that we did? We multiplied by 18.4 divided by 6.7. So it's this here. So if you weren't able to work that out, given that I worked out the final ratio here, I could just go along all of our options and figure out which one works out to 2.75. And it should be 18.4 divided by 6.7. Great. Part C. Lisa also wants to create a pattern on a wall. So she's got a leaf, and then she's going to turn the leaves clockwise. And how many leaves does she have? 1, 2, 3, 4, 5. So on what angle does she need to turn the sticker? Okay, so essentially, if we're going to rotate, this is my object here, and I'm going to rotate it around, I can only rotate on a circular axis, right? So I can only move this, thing around, essentially around the circle, right? So everything's got its own, circular axes. We can only rotate it around that circular axis, right? So if you ever use Photoshop or something, you'll, hopefully that will help you understand what I'm talking about. If not, that's okay. But essentially everything rotates around a circular axis, which is 360 degrees. So essentially, if we want to have 5 little, arrows evenly spaced out, we're going to have to rotate them evenly around our circle. So if we have 360 degrees and we want to have an equal share of 5, things around the circle, all I'm going to do is take my circle and divide it evenly into 5 splits, right? So that's 360 divided by 5. So 360 divided by 5 is, 72 degrees. So essentially what that means is if I have my circle and I put everything 72 degrees, away from each other, so a distance of, well, maybe not a distance, but yeah, if we angle it, keep rotating 72 degrees each time, we'll end up back here, and this is going to be some kind of, even split around our axis. So 72 degrees is the angle of rotation, if that makes sense. All right, and that brings us to the end of the paper. So thanks for watching. I apologize if you can hear the guy mowing the lawn outside. But yeah, I think that's all I wanted to cover. And thanks for watching, and I'll see you guys in the next video.